In our last lesson, we talked about Gauss's lemma, and today we are going to move on towards Gotthold Eisenstein's work, and specifically how he built upon Gauss's lemma to make a bridge between talking about quadratic residues and counting lattice points on a triangle. And the proof that we will go over next class about the law of quadratic reciprocity, because of Eisenstein's work, will be reduced to a sentence upon making that transition to geometry. And so this proof is beyond clever, it's very intricate, and it's just worth keeping that in mind, as it's one of these things that is just all the pieces just fit in nicely and we're able to make this connection. And Gauss was taken aback by this proof, and also the many proofs that Eisenstein published in his short life, and said that Eisenstein's talent is one that nature bestows only a few times a century. The same year that Eisenstein published his proof of the law of quadratic reciprocity, he also published 25 other articles, and each of these were revolutionary in number theory. Amongst these papers were the proofs of the law of cubic and quartic reciprocity, which had gone unsolved up to that point. To put this in perspective, in the exam, you considered a question about cubic residues, and in a similar fashion, one can then make a conjecture about what is the law of cubic reciprocity, or the law of quartic reciprocity when we were now looking at perfect fourth powers. And this was something that Gauss had moved his attention to after his work in 1796 on the law of quadratic reciprocity. He aimed to prove the law of cubic and quartic reciprocity, but was unable to. And here comes Eisenstein in 1844 and proves not just cubic, but as well as quartic reciprocity. At that point, Gauss was 67 years old and invited Eisenstein over to Göttingen for the summer, where they both worked. And Eisenstein's background he came from poverty, struggled throughout his life, had lots of health problems, which would eventually lead him to pass at a young age of 29 from tuberculosis. But in that time, through Gauss, who advocated for him amongst other mathematicians such as Humboldt, he was able to get a professorship, he got an honorary doctorate. Gauss got him elected to the Academy of Göttingen, and as a professor, he actually taught a young Bernhard Riemann, and Riemann would later generalize the work of Eisenstein, leading to what is known today as the Riemann hypothesis. And so let us go ahead and get started and start building upon the ideas that we need to be able to make this bridge that Eisenstein created between quadratic residues and geometry. So our first definition is non-standard, but it will make the presentation of Eisenstein's lemma smoother in having a language to discuss this. So let's go ahead. For an odd prime number p, and a an integer not divisible by p, we are going to define the Eisenstein value of a at p, which we denote by t of a comma p, to be the quantity q1 plus q2 all the way to q sub p minus 1 over 2, where these q sub k's are the unique integers determined by the division theorem, in such a way that we have a times k is equal to p times q sub k plus r sub k, where we have that r sub k is the remainder between 0 and p, but we're choosing the k's to be between 1 and p minus 1 over 2. So let's go ahead and do an example just to get familiar with this terminology. And I do apologize, I noticed that over here it looks like a p to the a, but that's just the footnote that I put over here is referred to as a, but this is not p to the a, it's just p. So let's go ahead and compute 25, the Eisenstein value of 25 at 7. And so by definition, we need to compute these quantities q1, q2 all the way to q p minus 1 over 2. And so here, p minus 1 over 2, since we're dealing with 7, this will be 7 minus 1 over 2, so we're just going to go to 3. So this here is going to be some q1 plus q2 plus q3. And now these qj's are determined by looking at a times k and then having this be equal to P times QK plus RK where we're applying the division theorem. So the first case, what we want to do, we have A is 25 for us. And we have that our possible K values are 1 through 3. And so what we are going to do is consider 10. So this is 10, not 10, 25. That's our A, times 1. We have 25 times 2, and then 3 times 25. And we want to apply the division theorem to each of these, where we're applying it to 20, the number on the left, and then with 7. And so over here we're going to have Q1, Q2, and Q3, and then we're going to have a remainder from the division theorem. So let's go ahead, compute these, and what we get. So we have this here. So now I've applied the division theorem. For the 25, we're going to have 3 times 7, 21 plus 4. Then 49 plus 1 will give us 50. And 70 plus 5 will give us 75. And so we got our Q1, our Q2, and our Q3. And so now we can go up here. And so we have that the Eisenstein value of 25 at 7 is just going to be 3 plus 7 plus 10. And so we get back 20. And so that's the evaluation. And so what Eisenstein's lemma says is that if we have a not prime p, and a is an integer not divisible by p, then if a is odd, then a on p is equal to -1 to the Eisenstein value of a at p. But before we prove this, I'm going to go through and do a numerical investigation that will motivate the abstraction and the symbol pushing that we are about to undertake. And so let's do a concrete example to see why this is true, as that will motivate the proof argument that we are about to do. I also recommend looking at page 505 of the text. So there is a Naomi's numerical proof as well that goes over Eisenstein's lemma and working about this numerically. So let us go ahead and revisit the example we just did. But now go through it in the same manner that we are going to prove Eisenstein's lemma. Because what is going to happen is that the proof for Eisenstein's lemma is this numerical example we are about to do, where we replace everything with a symbol. And that's going to be the proof. And so let's do an example, as this will give us an intuition for what is happening. But first, let's go ahead and verify that according to Eisenstein's lemma, we have that the Legendre symbol of 25 on 7 is going to be -1 to the Eisenstein value of 25 at 7. So -1 to the 20, so we get back +1, so this should be 1. We can also see it from Gauss's lemma, because in our case we have p is 7, and so p minus 1, which is 7 minus 1 over 2 is going to be 3. And if we look at 25 times 1 bar, 25 times 2 bar, then 25 times 3 bar, stop. We already got the remainders mod 7, 4, 1, and 5. And so this here is going to be 4, this is going to be 1, and this is going to be 5. But that tells us that there are 2 negative residues, namely 4 and 5. So G is equal to 2. And so Gauss's lemma tells us that this is -1 squared, which is 1. And so this matches up with what we expect so Eisenstein's lemma matches up with what we expect from Gauss's lemma. So how would the proof go? How are these things related? How can we go from G to this Eisenstein value of 25 at 7? So the first thing is we're going to go ahead and consider the following. We're going to go from J equals to 1 to 3. And just to be consistent, I'm going to put K. Actually, K equals to 1 to 3. And we're going to do 25 times K. And so all we're doing is what we just did earlier. We did 1 times 25, 2 times 25, 3 times 25. But now let's go ahead and add these up, and we get. So this is just adding them together, but for all of these, we of course have a common factor of 7. So we can factor out that 7, and we're left with 3 plus 7 plus 10. But that's our value for t of 25, 7. So we have here 7 times t, 25, 7. Eisenstein value of 25 at 7. And now what we are going to do is replace the 4 and the 5 and look at it as 4 minus 7. And then the 1 will stay the same. And the 5 is going to be 5 minus 7. And this is just so we can get the negative residues into a positive residue. So 4 minus 7 is still congruent to 4 mod 7, and 5 minus 7 is still congruent to 5 mod 7, so we haven't changed this. But if we want to maintain the equality, and this is crucial, if we want this to maintain the equality, we're subtracting one 7 and another 7, so we need to put in a 2 times 7. So we got this here. So now, by doing this subtraction, we're preserving the equality. But now this 2 is counting the number of negative residues, because that's exactly when we put in that minus 7. So that's G. And so now we have 7, T25, 7, minus 3 plus 1, and then minus 2, and then I'm going to write this as a plus 7G. So we got this here. And so here's the brilliance of Eisenstein's approach to this. Let's go ahead and consider this here and this 1, 2, 3 separately. And so here we are, we have the 25, and instead of writing it in this sum, I have 1 plus 2 plus 3. But over here we have minus 3 plus 1 minus 2. And let's make the following observation when it comes to modulo 2. A is congruent to its additive inverse, mod 2. Because if we have an integer and we reduce mod 2, we have that number is going to be congruent to 0 mod 2 if it's even, or 1 mod 2 if it's odd. And as a consequence, we have that reducing mod 2, if we change, it does not affect the signs. So namely, A is congruent to minus A mod 2. And so over here, if we reduce this mod 2, 25 is odd, so it's going to be 1 mod 2. And so this portion over here is going to be congruent to just 1 plus 2 plus 3 mod 2. But now this portion over here is going to be congruent to 1, well, right in there. Negative 3 will be congruent to 3. Then we have the 1, and the minus 2 is going to be congruent to 2 mod 2. And of course, we can go ahead and just cancel them off, but I'm going to leave it in this way. Because what Eisenstein then realizes that if we reduce mod 2, we always have the k minus 1 to 3 of 25k is congruent to the portion over here, which is just going to be counting down to 1, 2, 3, in our case. But by Gauss's lemma, we know that the list from a times 1 bar, a times 2 bar, all the way to a bar times p minus 1 bar over 2, that can be rearranged into the list 1 bar, 2 bar, 3 bar, all the way to p minus 1 over 2, so long as we omit signs. And so this is the theorem that came right before the proof of Gauss's lemma. We can rearrange this list, and so that's what we are seeing right now. We have 1, 2, and 3 appearing. But modulo 2, we omit the signs. And so we have that this here is congruent to this mod 2. So now let's go ahead and use that fact and reduce the whole thing, this whole equation, mod 2. And so we have that k equals 1 to 3 of 25k is congruent to 7, but 7 is odd, so we're going to be we're reducing mod 2. Since 7 is odd, 7 is congruent to 1 mod 2, so that's just going to be the Eisenstein value of 25 at 7. Then we have the plus 1, plus 2, plus 3, corresponding to the negative 1 plus 1 minus 2. And then we have the plus 7g. But now, 7, again, prime, congruent to 1 mod 2, so that's just going to be plus g mod 2. But we just said that 25k the sum from 25k from 1 to 3 is congruent to 1 to 3 mod 2. This is a ring. Working modulo 2, this is a ring. So we can go ahead and subtract off, since these are equal, they're going to cancel off. And so what we are left with is that we have 0 is congruent to t of 25, comma 7 plus g mod 2. And consequently, if we bring the g over to the other side, negative g is still congruent to g mod 7. Sorry, g mod 2. So we have that this is going to be congruent to g mod 2. So that means that g, the sign of g, is the same, the parity of g is the same as the parity of t of 25, 7. And as a consequence, the Legendre symbol will match up because negative 1 to the g, this exponent only depends if it's even or odd. Now we know that t of 25, 7 has the same parity as g. And so in this case, since this is 20, it's even. Negative 1 to an even power is 1. The Legendre symbol is 1. Now what we are going to do is do this same exact argument, but now do it by replacing everything with symbols. So we are assuming now p is an odd prime. A is an odd integer, so we're assuming a is also odd, and it's not divisible by p, and we want to show this. So the first thing is, we want to look at that sum. So we want to consider the Eisenstein value of a at p. But to do so, so by the division theorem, so let me write this. For k, a natural number with 1 less than or equal to k less than or equal to p minus 1 over 2, let rk and q sub k be the unique integers given by the division theorem so that k times a is equal to p times q sub k plus r sub k. So we have this here. So by definition, we have that the Eisenstein value of a at p is equal to the sum from k equals 1 to p minus 1 over 2 of the q sub k. So that's the definition of this. So now what we are going to do is let s sub k be the following. So let s sub k, and so this is going to be a shorthand way of keeping track if it's a negative or positive residue, modulo p. So we're going to let s sub k be equal to r sub k if 1 is less than or equal to r sub k, less than or equal to p minus 1 over 2. And if it's not the case, so we know that we applied the division theorem, so I forgot to mention this part over here. But by the division theorem, we know that each r sub k is at most p. So here we have rk minus p, and now here we have p minus 1 over 2 less than rk less than p. And so we have our s sub k. And now what we are going to do is sum all the ka's from 1 through p minus 1 over 2. And so we're doing the sum from k equals 1 to p minus 1 over 2 of k times a, but this is just going to be the sum from k equals to 1 to p minus 1 over 2 of p qk plus r sub k But now, this is going to be the same. If we break this up into two parts, we're going to have the sum of p times q sub k plus the sum of the r sub k's. But each of the p times q sub k's has a factor of p, so we can factor it out, and we are left with the sum of the q sub k's, which is the Eisenstein value of a at p. And so we're going to have that plus the sum of the r sub k's. And so we have this. But now when we look at this here, we are back in this stage of the numerical example we did earlier. We have t of 20, in this case it was t of 25,7, but now we have our t of a comma p. And then we have our remainders. But then we want to count those negative residues. And what we did was we put a minus p, so in this case minus 7. And then because we have to do that each time we have a negative residue, which will be counted by g, we're going to have the prime appearing g times, and so we're going to have a plus p times g on the right. And so this is where the s of k notation comes in, because now we have p times this plus k equals 1 to p minus 1 over 2 of the s sub k's plus p times g. And so we got our value here. So now we're going to proceed just as with the numerical example. So since k equals to 1 to p minus 1 over 2 of ka is congruent to mod 2, we know a is odd by assumption, so mod 2 is congruent to 1 mod 2. So this is congruent to k equals 1 to p minus 1 over 2 of k mod 2. And we also have that the sum from k equals 1 to p minus 1 over 2 of the s sub k's, that this is going to be equal to, congruent to, k equals to 1 to p minus 1 over 2 of k mod 2 by Gauss's theorem. And so here we're using theorem 1.17.1. We have this here, and we are looking at this. We went ahead, subtracted we subtracted from the negative residue so that we could have everything appearing from 1, 2, all the way to p minus 1 over 2. And so we have that all those numbers are appearing up to sign. So it may be that it's the case that the negative is occurring. In the same way that we saw with our numerical example, we had a negative 3 and a minus 2, but now in the same situation, so here we have 117.1. We now have that this is all the cases from 1 to p minus 1 over 2. So this and the sum of the KAs and the sum of the SKs are congruent modulo 2. And so therefore, we get the following, that the sum from k equals 1 to p minus 1 over 2 of the KAs, this is congruent to p times, so now we're reducing mod 2. P is odd, so it's congruent to 1 mod 2, so we just have the t, a comma p mod 2, plus, we have our sum over here, so we have this next, of the s of k's, and then plus p times g, but p is odd, so that's just going to be g mod 2. But because these over here are the same, mod 2, we get that this is congruent to 0. And so the left hand side is going to be, we can cancel out, and we have t of a comma p plus g mod 2 is congruent to 0, which is the same as t of a comma p is congruent to g mod 2. And so consequently, -1 to the g is going to be equal to -1 to the t of a comma p. But we know by Gauss's lemma that -1 to the g is the Legendre symbol for A on P. And so now we have A on P is equal to -1 on G. So this is Gauss's lemma. And by what we just saw that T of A comma P is congruent to G mod 2, so they have the same parity. G is even if and only if T of A comma P is even. And so both of these will be equal to each other. And so we have now proven Eisenstein's lemma. We now have that this Eisenstein value of A at P has the same parity as G, and we have a new way of computing the Legendre symbol. So now let's tie that in with lattice points. So now we're going to build up to our geometric interpretation. So our first definition on this end, we're going to say that a pair x, y is a lattice point if x, y, this tuple, both of them are integers. So x, y are both integers. So when p is an odd prime and a is an integer not divisible by p, we're going to say the Eisenstein triangle determined by a and p, which we're going to denote by delta of a comma b, is the right triangle in R2 whose vertices are 0, 0, p over 2, 0, and p over 2, a over 2. So notice p is odd, so p over 2 is not an integer. And in practice, even though it's not part of the definition, when we are applying it, a will also be odd. And so we will have that a over 2 is also not an integer. So let's go ahead and consider what is the Eisenstein triangle of 25 and 7. So the Eisenstein triangle determined by 25 and 7, since this harkens back to our earlier example where we computed the Eisenstein value of 25 at 7. So here's our Eisenstein triangle for 25 and 7, and I just noticed a typo. It was supposed to be delta of a comma p instead of delta of a comma b. So 25 over 2, of course, is 12.5, and 7 over 2 is 3.5. So here's our Eisenstein triangle. It has vertices 3.5, 0, and then we have our next vertex, which is going to be 3.5, 12.5, and so we have our triangle. And now what I want you to do is to pause the video and count the number of lattice points that we have in the interior. And so the nice thing is that now we actually can see which are the lattice points, because the way that the scaling has been done, we have 1, 0, 2, 0, 3, 0. Bit of a note over here, this is not in the interior, and so we have 1, 2, 3 over here, and then that's it. So go ahead, count these, and so note that there's one over here that is not on the boundary, so it's in the interior of this triangle. So count them, see what you get. Pause the video. So you should have gotten 20, and we can actually see that here, if we went ahead, colored these yellow, so we have 3 over here, we have 7 going up, and then finally 10 up to there. 3 plus 7 plus 10, 20. But that was the Eisenstein value of 25 at 7. And that's the bridge for all this work that Eisenstein did, was make a connection with this T of 25 at 7, which we already know is related to the G appearing in Gauss's lemma. But now it's counting the number of interior lattice points of the Eisenstein triangle being determined by these two quantities. And that's the next proposition, is to prove that this is true. So if we have a odd prime number p, a is a natural number not divisible by p, then the number of lattice points in the interior of the triangle of delta a comma p equals t of a comma p. So one thing I want us to observe before we do the proof is that the numbers of interior lattice points, when we counted them in this direction, they were exactly the numbers q1, q2, q3 that we computed, 3, 7, and 10. And so that's how the proof is going to be built, is using that interpretation that we got from the Q1, Q2s, and Q3s, and making a connection to that these are the lattice points when we look above 1, 2, and 3. As that is what is happening here. Above 1 we had 3, above 2 we had 7, and above 3 we had 10. So let's go ahead and prove Eisenstein's proposition. So here's our Eisenstein triangle, and we want to count the number of interior lattice points. So, first thing, so note that if k comma j is a lattice point in the interior of the Eisenstein triangle, then we have that k has to be between 1 is less than or equal to k, which is going to be less than, strictly less than, p over 2. Because p over 2 is not an integer. And also, we're not counting points on the boundary. We only want the interior. So even if it was an integer, we will not be including it. And so we're going all the way up to p over 2 for k. And then now the j is the y-coordinate. The greatest y-coordinate we can have is a over 2. And we have 1 is less than or equal to j, which is less than, strictly less than, a over 2. And so we have these here. And so these will be the conditions that the lattice point must satisfy. But now, what is the greatest integer, k, that is less than p over 2? Well, it is p minus 1 over 2. So we can write that as the floor function of p over 2 is equal to p minus 1 over 2. And thus, we have that 1 is less than or equal to k, which is less than or equal to p minus 1 over 2. And so we have this part over here. So next, we're going to go ahead and consider the Eisenstein value of a at p. And so this is q1 plus q2 all the way to q sub p minus 1 over 2, where we have that a k is equal to p times qk plus the remainder, with rk being less than or equal to, greater than or equal to 0, but strictly less than p. So we have this here. And now let's go over to the triangle and ask, what is the slope of this? We know that the coordinate over here is p over 2 comma a over 2. And so what we end up getting is that the slope for this equation is going to be a over p. So the slope is going to be equal to a over p, and therefore the equation of the line is going to be equal to a over p times x. And so here's the intuition for what we are going to be doing. Our k, our x, we want to plug in integer values, and we know now we have a bound for what our value can be based on a over p times x. That's going to give us the y entries over here. So we want to have, if we plug in k x equals to 1, we're going to have just y is equal to a over p, and that gives us a bound for how many lattice points we can have going up for each k value. And so what we are going to do now to make the connection is we're going to divide this equation here by p. Because in doing so, we're going to introduce a over p on this end. So dividing by p yields a k over p equals qk plus r sub k over p, where we note that because r sub k is between 0 and p, this is going to be a rational number that is strictly less than 1 and greater than or equal to 0. So where rk is less than 1, so we have this here. But now as a consequence, we have that the greatest integer less than ak over p has to be q sub k. But now, this tells us that if we fix k, so then for a fixed k, we have that the following set of k comma j, where j goes from 1 to q sub k, that these are lattice points. In the interior of our triangle. And so now we are essentially done, because this set consists of exactly q sub k elements. So the cardinality of this is q sub k. And we're doing this for a fixed k, where k is between 1 and p minus 1 over 2. So the total number, so therefore, the total number of lattice points in our triangle is the sum of q1, q2, all the way to q sub p minus 1 over 2, but that's the Eisenstein value of a at p. And we are done. And so now we have made this connection that we have the total number of lattice points in the interior of this triangle is equal to this t of a comma p, which we have related already to Gauss's lemma. And now we are just partway there to proving the law of quadratic reciprocity, which will be the content of the next video.